Hello everyone, welcome back to part 3 of our cloud security system. In part 1, we discussed cloud security risk, threat agents, cloud security threats, and in part 2, we discussed different cloud security mechanisms. Now, in this part, we will continue with some important authentication and virtualization security concepts. Now, let us continue with the next topic. Now, let us begin with authentication. Authentication is the process of verifying whether a user or message is genuine. In simple words, authentication answers the question, are you really who you claim to be? For example, when you enter your username and password into Gmail or online banking, the system verifies your identity before granting access. This slide also mentions two types of authentication. The first type verifies the identity of a user or application participating in a session. The second type verifies the sender of a message. Kerberos is an authentication protocol that uses symmetric key encryption and a key distribution center for secure communication. The Kerberos authentication server stores the secret keys of users and also maintains information about which users are allowed to access which network services. Now, let us understand the basic idea behind the Kerberos authentication protocol. Kerberos works using a trusted central server called the Key Distribution Center. Instead of directly sending passwords across the network, Kerberos uses tickets for authentication. Think of it like entering a movie theater. At the entrance, you first verify your identity and receive a ticket. Then you use the ticket to access different areas without repeatedly proving your identity. Similarly, in Kerberos, once the user is authenticated, the system issues a special ticket that is later used to access services securely. First, the user sends the login credentials to the authentication server. After verifying the credentials, the server generates a ticket granting ticket, commonly called TGT. This ticket acts like a temporary identity proof for the user. Instead of sending the password repeatedly, the user later presents the ticket while requesting services from the ticket granting server. Now, the ticket granting server verifies the ticket granting ticket provided by the user. If the ticket is valid, the server issues another ticket called the service ticket. This service ticket is specifically meant for accessing a particular cloud service or network resource. So, Kerberos avoids repeated password transmission and improves authentication security. In the final stage, the user presents the service ticket to the required service. The service verifies the ticket using its shared secret key. If the verification is successful, access is granted to the user. So overall, Kerberos provides secure authentication using symmetric key encryption, ticket-based verification, and centralized authentication management. Now let us discuss one-time passwords, commonly called OTP. An OTP is a temporary password used for user authentication. Unlike normal passwords, an OTP can be used only once and becomes invalid after a short period of time. We commonly see OTPs in online banking, payment applications, email verification, and login authentication systems. For example, when you make an online payment, the bank sends a unique code to your mobile phone. Only after entering that OTP is the transaction completed. This improves security because even if someone steals the OTP, it cannot be reused later. OTPs can be sent through SMS, email, phone calls, authenticated apps, or push notifications. This slide explains the two main methods used to generate OTP. The first method is time-based OTP, also called TOTP. Here, the OTP is generated based on the current time. For example, the password may change automatically every 30 seconds or every 1 minute. Both the user device and server use the same secret key and synchronized clock to generate matching OTP values. The second method is event-based OTP, also called HOTP. Here, OTP generation depends on a counter value instead of time. Each time a password is generated or used, the counter increases. So both the user and the authentication server must maintain synchronized counter values. These OTP generation methods help improve authentication security in cloud systems. In based OTP systems, the password remains valid only for a short duration, such as 30 seconds or 1 minute. After the time expires, the OTP automatically becomes invalid and a new OTP must be generated. This reduces the chance of attackers reusing stolen passwords. In the case of event-based OTP systems, the OTP remains valid until it is used or until a new counter value is generated. So, compared to time-based OTP, event-based OTP provides slightly more flexibility for users. This slide explains some important OTP authentication features. First is single use. An OTP can be used only once. After successful authentication, the same OTP becomes useless. Next is synchronization. For HOTP systems, both the user and server must maintain the same counter values. For TOTP systems, both sides must maintain synchronized clocks. This slide also mentions about token devices and apps. OTP must be generated using hardware tokens, mobile authenticated apps, or software-based generators. Finally, OTP delivery methods must also be secure to prevent interception during transmission. Now let us see the benefits of OTP. The first benefit is enhanced fraud and data protection. Since OTPs expire quickly and work only once, attackers cannot easily reuse stolen passwords. The second advantage is scalability. OTP systems can be used globally on mobile devices and cloud applications. The final advantage is convenience and ease of use. Users can quickly authenticate themselves using mobile phones, authenticated apps, or email verification methods. Now, let us move to another important topic called virtual machine security. As we know, cloud computing heavily depends on virtualization technology. Multiple virtual machines or VMs run on the same physical hardware using a software layer called the hypervisor. This explains two approaches for providing security in virtualized environments. Now look at the diagram shown in this slide. Here, security services are directly provided by the hypervisor itself. The hypervisor acts like a central controller, managing all the virtual machines running on the physical server. Think of it like a security guard monitoring multiple apartments inside the same building. Since the hypervisor controls the virtual machines, it can monitor activities, manage isolation, and provide security functions for all virtual machines together. In the second diagram, in this approach, instead of the hypervisor directly handling all security tasks, a separate dedicated virtual machine is created specifically for security services. This dedicated security VM performs tasks such as monitoring, malware detection, logging, and security management. You can think of it like a separate control room inside a building that continuously monitors CCTV cameras and security activities. It also mentions an important concept called TCB, which stands for Trusted Computing Base. TCB refers to the trusted components responsible for maintaining security in the system. If the TCB itself becomes compromised, then security of the entire virtualized environment gets affected. So maintaining a secure hypervisor and trusted virtualization environment is extremely important in cloud computing. This slide continues the discussion on virtual machine security. Hypervisors are generally less complex and more structured compared to traditional operating systems, which helps improve security management. However, there are still some challenges. A hypervisor mainly sees low-level raw data of virtual machines whereas security systems usually work at higher levels like files, applications, or user activities. There are some important advantages of virtualization. Since the hypervisor controls all virtual machines, it can save virtual machine states, restore them, clone virtual machines, and even encrypt them. Cloning becomes very useful for security analysis. For example, suppose a suspicious application is found inside a virtual machine. Instead of directly testing it on the original system, the virtual machine can first be cloned and tested separately to observe its behavior safely. Similarly, dangerous applications can be examined inside cloud environments without affecting the real system. There is another security advantage where virtual machine files can be moved to a dedicated virtual machine for better protection against attacks. So, virtualization not only improves resource management but also provides useful security capabilities. This slide explains the cost and challenges associated with the virtualization security. Although virtualization improves security and flexibility, it also introduces additional overhead. First, virtualization requires higher hardware resources such as CPU power, memory, storage, and network bandwidth. This increases infrastructure cost. Second, developing and maintaining hypervisors also requires additional effort and cost. It also mentions about virtualization overhead because the hypervisor participates in many privileged operations between virtual machines and hardware. The next slide it introduces Terra, which is a virtual machine based trusted computing platform that uses a trusted hypervisor to securely partition resources among virtual machines. Finally, the NIST security group classifies virtualization threats into two categories. One is hypervisor-based threats and virtual machine-based threats. These threats will be discussed in the next slides. Now let us discuss hypervisor-based threats. These are attacks that target the hypervisor layer which controls multiple virtual machines in a cloud environment. One major threat is resource starvation or denial of service for certain virtual machines. For example, if one rogue virtual machine consumes excessive CPU, memory, or bandwidth, other virtual machines sharing the same hypervisor may become slow or unavailable. This can happen due to poor resource configuration or malicious VMs bypassing resource limits. This slide also mentions VM side channel attacks. Here, a malicious VM tries to gather information from neighboring virtual machines running under the same hypervisor. This may happen because of weak isolation between virtual machines, insecure virtual networks, or outdated virtual machine images without proper security patches. Another important threat is buffer overflow attack, where attackers exploit memory handling vulnerabilities to compromise the system. So overall, vulnerabilities in the hypervisor layer can affect multiple virtual machines simultaneously. Now let us discuss virtual machine based threats. Unlike hypervisor based threats, these attacks mainly target the virtual machines themselves. One important threat is the deployment of rogue or insecure virtual machines. For example, unauthorized users may create insecure virtual machine instances or misuse administrative privileges to launch malicious virtual machines inside the cloud environment. This usually happens because of poor access control over virtual machine management activities such as virtual machine creation, launching, suspension, or reactivation. Another major threat is the presence of insecure or tampered VM images in the VM image repository. Think of VM images like templates used to create virtual machines. If attackers modify these templates by inserting malware or vulnerabilities, every virtual machine created from that image may also become insecure. This can happen due to lack of proper access control or absence of integrity verification mechanisms such as digitally signed VM images. So proper virtual machine image management and access control are very important in virtualization security. Now let us discuss some security advantages of virtualization. The first advantage is support for the IaaS delivery model. Virtualization allows users to easily create, upload, and run virtual machine images according to their application requirements. Next is improved system reliability. Virtual machines can be duplicated and maintained as standby systems. If one virtual machine fails, another virtual machine can quickly take over, improving fault tolerance. Another important advantage is efficient resource management. Virtual machines can be moved between physical servers to balance workloads and reduce power consumption. The next one is enhanced intrusion detection. Cloned virtual machines can be used to safely monitor suspicious activities or test potentially dangerous applications without affecting the original system. The next advantage is secure logging and monitoring. Since monitoring can be done at the hypervisor level, attackers inside a virtual machine cannot easily tamper with security logs. Finally, virtualization simplifies software maintenance because multiple operating systems and software versions can run on fewer physical machines. So, virtualization provides many advantages. It also introduces several security challenges. The first issue is virtual machine sprawl. Creating a virtual machine is very easy. Sometimes it is as simple as copying a file. Because of this, organizations may lose track of how many virtual machines are active, making management and security updates difficult. Another challenge is non-uniform software environments. Different virtual machines may run different operating systems and patch versions, making it difficult to apply consistent security policies. This slide also mentions about complicated patch management. Unlike traditional systems, virtualization environments may contain many virtual machine branches and cloned systems, so maintaining updates becomes more complex. Another serious problem is persistent malware threats. Some infected virtual machines may remain inactive during malware cleanup. Later, when these dormant virtual machines become active again, the infection can reappear. Finally, virtualization environments may never reach a completely clean steady state because inactive or poorly managed virtual machines may continue carrying vulnerabilities. Now let us discuss some new security vulnerabilities introduced by virtualization. The first issue is virtual machine rollback vulnerability. Virtual machines can be restored to earlier saved states. While this is useful for backup and recovery, attackers may misuse it to access old credentials or reuse previously valid authentication information such as OTP. This can even lead to replay attacks or session hijacking. The next problem is loss of identity tracking. Since virtual machines are dynamically created and may use random MAC addresses, tracing malicious systems becomes more difficult in virtual environments. Another important issue is confidentiality and data residue. Even after data is deleted, sensitive information may still remain inside physical disks, virtual machine snapshots, or backup files. So, virtualization introduces additional security challenges that must be carefully managed in cloud environments. Now, let us discuss the concept of a trusted hypervisor using the Terra architecture. The main goal of Terra is to improve security in virtualized environments. There are two types of virtual machines. One is open box virtual machine and closed box virtual machine. Open box virtual machine allow inspection and full access by the platform owner. These are suitable for normal purpose applications. Closed box virtual machine are designed for highly secure applications such as banking or electronic voting systems. Here, even the platform owner cannot inspect or modify the virtual machine contents. This slide also explains that applications can choose different software stacks depending on security requirements. High security applications may use a minimal operating system with only essential components, while general purpose applications may use full featured operating systems. Another important concept mentioned is the trusted path. This creates a secure communication path between the user and the virtual machine, helping both sides verify each other's identity securely. Overall, Terra strengthens virtualization security by providing better isolation, confidentiality, and trusted communication. This slide continues the discussion on the trusted hypervisor in the Terra architecture. One important feature is remote attestation. This allows a virtual machine to prove its identity securely to remote users or cloud services. It helps establish trust between virtual machine and external systems. It also discusses protection against malicious device drivers. Device drivers are often vulnerable because they are large and frequently modified by vendors. Terra restricts these drivers from accessing sensitive information directly. Hardware-level memory isolation is also used to prevent attacks such as DMA-based attacks where malicious devices try to access system memory illegally. Another important feature is hypervisor isolation from the platform owner. Even the system administrator or platform owner does not get direct privileged access to the hypervisor. This creates strong isolation and protects the integrity of all running virtual environment. In the Terra architecture, a special management virtual machine is created to handle administrative activities securely. You can think of it like a control room inside a large building. Instead of allowing every person direct access to important systems, the control room manages and monitors everything centrally. Similarly, the management virtual machine controls how many guest VMs can run, which VM can access hardware resources, and whether a VM is authorized to launch or not. This helps prevent insecure or unauthorized virtual machines from entering the cloud environment. Terra also provides guest virtual machines with a virtual hardware interface. So even though the virtual machine is not directly interacting with the physical hardware, it still receives controlled access to virtual network interfaces, devices, CPU, memory, and other system resources. This creates strong isolation and allows applications to run securely without interfering with other virtual machines. So with that, we come to the end of this cloud security session. Thank you.